you'll see the mesh following the curves precisely. But yes, the surfaces do not, they're using a sort of a coarser representation of the surfaces than what is really there. And, you know, that's just, that is, I guess, a feature of Qubit, is that it's going to simplify things in the display. But you'll notice in the mesh that the mesh really did follow our.
Okay, I'll go ahead and get started with our 3D example. And so for this example, rather than using curves to divide things up, we're going to use surfaces. And to do this, right now, for instance, we've made up a little fake problem where we have points on the surface. And for instance, for our subduction interface, we have just this set of points. And what you can see is that what we have contours here. So here's the 80-kilometer contour, 60, 20, and then our last contour is actually up in the air because we want our interface to intersect topography and bathymetry. So to make sure of that, we put points that are up above that. So we're going to use two different methods of generating surfaces within Qubit. This first one I'm going to show, this is called a net surface, and that's when you're able to have sets of intersecting lines. For instance, in this case, we have contours forming one set of lines, but if you transpose these numbers, we also have profiles. And so what we do, going from this set of points, what I've done is I have a really simple Python script here that takes these points in, and then all it does is creates a set of contours, and then the points per contour would be your profile. So it is going to create the Qubit commands that would make these spline curves, and then using these spline curves, we're going to use create what's called a net surface. That's what happens when you can do intersecting curves. So all we do here is form these points into curves using this create curve spline command that we use for the 2D. And we'll then just loop over the contours and the profiles. And then once we've done that, then we'll create our net surface. So when we do that, here I'm going to now go back. This might be, I'm just going to bring Qubit over here so we can see it. First we'll clear everything out of Qubit. We'll just do reset. We're going to clear all of our apropos variables, as we'll redefine some of them. I'm going to quit out of this journal editor. I'm going to set the directory, the one that we're working on now. And now we'll open up a journal. The journal file that we just created. First, I should run the Python script. I'll show you that. And you can just do Python that. And that will create this interface netsurf.journal file right here. That's what we're going to open up. So by running the Python script, all I did was create this little file. And so here, we're defining the contours. These first 4 lines are creating spline curves that make the contours. And then these last 3 are forming the profiles. So we'll just do all of that, and then we're going to create a net surface using those. So I'll just show that part right here. Okay, this takes a little while to create the net surface, so if you have any questions while that's running. So you see these.
Charles, I wanted to mention that I got my qubit set up with the end result. So when you're done with all the geometry sitting there waiting, you can switch to my qubit.
Yeah, I have like a 5-year-old laptop, so it needs it takes a little while to run on here. So anyway, that's in the meantime, what I can show is that we're going to do similar. There we go. That wasn't too bad. So there's our net surface that we created. So using these contours and profiles, we made a net surface that reflects, that's our subduction interface geometry. Now we're going to do, I've already run these Python scripts to create the journal files. We have another one for display surface and for topography and bathymetry. The only difference with the display surface is that in this case, rather than a net surface, we're going to this is using a skin surface. So this is when you only have one set of lines to make your surface. So in this case,
Can you demonstrate how to run
Sure.
the Python script?
All you have to do is go into a terminal, and you can just type Python display skin surface.py. And once you've done that, it creates this journal file. So all the Python script does, it takes in the points that you're using, and then it really just reformats those points to make them into qubit commands that are within this journal file. So once you've done that, we'll see what the journal file looks like. It's this. So here's our journal file. Now we just have 1, 2, 3, 4, 5 curves, and we're going to, rather than doing a net surface, which we did before, we're going to do a skin surface, which only requires lines in one direction. They're more or less parallel to each other. So we'll do that. Let's see, let me see, did I save this last surface? Let me just double check before no, I didn't do that part. Let me finish up that part. So for the interface, we can delete those curves and export the ASIS nerve surface. Okay, so we've exported that. So now this surface is available to re-import back into Qubit whenever we need it. Now we're going to do a similar thing with this splay surface. We'll reset so we forget everything, and then we'll create a skin surface out of these curves. Okay, that went a lot faster because it's a simpler geometry. So now that's our splay fault right there. So we defined it in terms of a set of profiles. So now we can delete the curves that we used and export that as another ASIS merge surface. So there we go. Then the final one is the topography and bathymetry, and it's exactly analogous to the interface geometry, where now we have just a set of points that we can form into both profiles and contours. And again, we run this Python script to create this journal file right here. So we'll look at that journal file. And it's pretty much looks just like the one that we use for the interface geometry. So again, we're just going to create a bunch of spline curves that cross each other. There we go. That's our topography and bathymetry. We've just made a nice grid there. And then we'll create a spline curve out of that. So there, it's pretty subtle, but there is actually some variation in the, you can see a slight curve in that. So once we've done that, we'll go ahead, delete the curves, and export that NURB surface. Okay. So the reason we've been creating all these surfaces is so that we can create a three-dimensional geometry out of it. So now we'll go ahead and open up our mesh journal file, which is again our main journal file. This is where we just control the creation of the mesh, but the first thing it does is creates the geometry by playing back a geometry journal file. So if we look at that, right here. So again, we're using AfraPro. We're going to use SI units again. We're going to start off by defining a block. Here we give it the dimensions of the block. We save the ID number of that block. And then we're going to move the block so that it's conveniently located in the XY position with respect to our surfaces. And also we move it down so that we can just chop off a little bit of the top to create our volume. So we'll go ahead and just do all of that. So there's our block. We've created that using the cubic brick command. That was this command right here. We've saved the ID number of that volume. And then we're going to import all of the surfaces that we just created, the topography, interface, and then display fault. So it takes just a little while to import those. So there they are. So now we have our volume. I'll set it so I can select volumes now. I have to turn off the, oops. So now, volume 1. So we've imported those. The first thing we're going to do is to chop that volume with our topography and bathymetry, and then we're going to delete the volume that lies above there because we don't need that. And then finally, body 2 is your topography and bathymetry. Once we've cut the top off our volume, we don't need that body anymore, so we can delete that as well. We'll go ahead and do that. Again, that takes just a little while to run. What you'll find, once you're using NURB surfaces, they're really handy for defining complicated geometry, but logical operations like web cutting can take a while because there's a lot of calculations that Qubit has to do to compute the intersection of the surface with the different geometry. There goes that.
We're getting some questions from.
Okay, what's the question?
So Anthony tried to run the interface and got an internal ASIS error.
Really?
So one option is possibly that things were not reset, and so the curves, if you somehow didn't play all of the commands, if you somehow skipped this reset command, then the curves may be numbered differently, and so you could end up with something trying to create a net surface from curves that didn't intersect.
Yeah.
That's one possibility. He is using Trellis, so
Possible that,
we know it works.
Well, it shouldn't number curves differently, but there's really no telling. Yeah, the best.
Well, it could be if there's curves that already existed. That would create errors because the curve IDs are hardwired into the journal file.
Yeah. So first thing, do a reset. Make sure that reset, also delete all of your apropos variables. It's remotely possible that there's some conflict there. Okay, so now what we've done, we chopped off the top of this volume, which is still volume 1. So the top part, I believe, was volume 5. And then we've deleted body 2, which was our topography. We still have these remaining sheet bodies. Body 3, that's your interface, and then body 4, which is your splay fault. So the next thing we're going to do is to web cut volume 1 with our sheet surface 8, which is your subduction interface. And then we're going to delete the subduction interface because we then don't need it anymore. I'll be interested to see if Eric's able to get this to work or if there's some problem using Trellis for this. Okay.
Other.
Yeah, again, I think this one's even more complicated than cutting with the topography because it's a more complicated surface. And the one thing about Qubit so far, it doesn't really do much in parallel, so having a bunch of processors, well, for things like this, it certainly doesn't help. I think it can do a few operations in parallel, but not that much. So you're kind of just stuck until it finishes. I'm trying to think what else I can show while we're waiting. Yeah, one thing, these Python scripts, the only external package I'm using in those is Numpy, and I'm really not doing anything with that. The only reason I did that is because it gives me a really easy way of reading in the coordinates, which we're using this Numpy load text command. But if you start doing much with either pre or post-processing, you'll find it to be an amazingly useful package. You can do all sorts of linear algebra operations, reformatting your data. It's really very handy. Did I see another question pop up?
Oh, yeah, so Eric asks, when you made the surface, was it a requirement that they extend beyond the volume, or could they go?
It does have to extend at least to the edges of your mesh. If it doesn't, you can't, because what a web cut does is divides a volume into a couple more volumes. So if your cutting surface doesn't go all the way through, it won't work. So you'll notice that these surfaces that we're using, can I get back to this? Let's see if I can. There we go. You'll notice that these surfaces extend beyond the boundaries of our volume. Okay, so that one finished. So now I've created two new volumes. There's volume 6, volume 1. And now the final thing that we need to do is to web cut this remaining volume with our splay fault, which we'll create. We'll divide volume 1 into two new volumes. So then we'll do that. Again, this will take a little while, hopefully not quite as long as the last one, both because this is a simpler cutting surface and also this is a smaller volume that we're cutting, so hopefully it won't take quite as long. Okay, so that wasn't too bad. So now that's still volume 1. This volume stuck in between the other two is now volume number 7. And then we have volume number 6. So once we've done that, then we have to do the same thing we did in 2D. We imprint all these volumes so that they are aware of adjacent volumes, and then we're going to merge those together. So I'll go ahead and do that. Now again, unfortunately, this will take a little while to do. So we'll merge those, but then once we've done that, we've completely defined our geometry. For this particular problem, we haven't actually done anything complicated with our discretization size. We're going to mesh it using tetrahedral cells, and we're going to just use constant mesh size. So it's actually pretty straightforward. And I can't even remember. We do define blocks and node sets, but for this problem, you'll notice that this is not a true problem because in reality, we're going to want our boundaries for this mesh far away from where things are going on, which is along the faults here. So that for a real problem, what you would typically do is have this volume contained within a larger volume so that you could have a mesh that extended much further out from here. And you would embed this volume within the larger volume. So this is it's a toy problem, but it's not particularly realistic. So I'm wondering, Brad, you have the thing all meshed up? Should we just...
Actually, I deleted it. I thought you had gotten far enough along that we didn't need it, so I was trying to
debug. It's finished with no, it's at least partially through with the imprinting.
So Anthony reports that he's tried restarting Trellis, and he says actually before the curved splines look really weird before the surface skin.
Oh, maybe the spline curves did not. Maybe it uses a different method for drawing the splines, and the curves are not. Well, that could be a problem. Okay, so maybe the surfaces.
So if anyone has access to the Trellis documentation, if they could send us the snippets for the creating the splines as well as creating a net surface, we could then check it against Qubit 14 as well as older versions of Qubit.
To see if maybe something has changed. I can't imagine it would be too radical, but we're slowly making progress with the imprint. Okay, so the imprint looks like it's just about finished. Now we're merging. Okay, so it finished and it merged together 3 sets of surfaces, which are going to be this surface, and then this surface down here. So now that we've done that, we can look at the meshing file. And as I said, we're just using constant cell size. We're using tetrahedral meshing, and then we'll just do the whole thing. I may not do the smoothing in this case. I'll just go ahead and mesh this up. So parts of it mesh pretty fast, and then I think the complicated surfaces take a while to create the triangles. Any other questions while that's going on?
I found the Trellis documentation on the CSimSoft site, so I'm going to look up spline.
Yes, we could always try the free trial ourselves. Okay, so we're making progress with the meshing. Some of them just take a while. Okay, there we go. So now we've got our mesh. Now I'm not going to do what I did yesterday. I don't think I'm going to. I can show you what you would do. I'm worried that things will take a while. But what you would typically do, you would look at your mesh quality using whichever we like the condition number, and then you can display a graphical summary. I don't think I'll try that today because I don't want it to get hung up again. But once you do that, then you can decide, typically you're going to need to do some smoothing after that. And that's what we're doing, just one level of smoothing here, but sometimes what we'll do is create a loop where this beta tells it what to strive for as far as improving the condition number. We're using the condition number smoothing scheme. So you'll loop and start with a relatively high value of beta and then reduce it by a small amount within the loop. I'm not going to do that today just because of time constraints, but you do want to, if at all possible, get your condition number so that you don't have any cells with a condition number higher than 2, and the more you can reduce it, the faster your finite element model will run. So now we're going to just quickly look at the boundary conditions. So again, we're going to create blocks that are associated with each volume in the mesh. So volume 1 is going to be the plate, the overriding plate. Volume 6 is going to be the subducting slab. Then volume 7 will be the sediments. So here we have that. Do that. So we have now with our blocks, we have plate, our slab, and then our sediments. So that's what we need for material properties within Playback. Now we're going to create the node set that defines the subduction interface. And so it says surfaces 33 and 38. To do that, we'll first look at, let's see, we'll look at this volume. So you can see, we'll just draw that volume separately. And you can see what the surfaces are that compose that volume. So you can see 33 is the bottom part of the interface, and then 38 is the top part. So we'll put that in a group. So we've created that group, and then from that group we'll create a node set. And we're going to give it an ID number of 100. There we go. Then we're going to do the same thing for the display fault. But the thing is, in Pilot, we're not allowed to have intersecting faults. So first, we're going to have this group. We're going to put the nodes in surface 30 within there. But then we're going to remove any nodes that are already in the group subduction fault. So first, we have this. There's that. So there's a display fault. But then we're going to remove this set of nodes along here that are already within the subduction fault. Okay, so now, it's kind of hard to tell, but we've actually removed the nodes that are right on that boundary. That's why we use groups to start with, because we can do these logical operations, and then we can put them in a node set. Okay. All right, so I'm just going to quickly go through the rest of this, because the only difference is that we also create edge or boundary node sets that have the fault nodes removed, because also in Pilot we can't apply boundary conditions to fault nodes. So we remove those nodes from some of our node sets. So I'm just going to go through the remainder of our boundary conditions here. And there we go. So now these are all of our different boundary conditions. Once we've done that, we're done with the boundary condition part. And now all we have to do is export our XDIS file, which is now a three-dimensional file. And there we go. So, any questions about that while I'm getting ready for the next example?
You see evidence of typing, so it should be a couple.
I wonder if I should. What I'll do, I'm going to switch over here.
So the question is, in the journal file you were just in, there's a command said playback bc.journal. Does that playback the entire file rather than has been done line by line here? Yes. So so what Charles is doing is he's highlighting things using selecting with the left mouse button, and then he clicks on the right mouse button and just plays the selected file. If you can use the big right pointing green triangle at the top on any journal file to run everything within that journal file. And then the playback command is when you want to run the commands in another journal file from the current journal file you're in. So from our mesh journal file, we're playing the geometry journal file. And so he can select that and right click on that rather than having to open that file. But generally what he's going to do is he's going to, in normal operation, he's going to sort of get his geometry file all set up. And that's why usually you put all of your commands related to geometry in one file and then all of your mesh generation stuff in another file, so that once you have the geometry file set up, you can just, if you want to just recreate all that, you just quickly play the geometry file. And then let's see, the other question is, what is the region, the example? So this, you mean which directory? This is in 3D. Where is it on the Earth? It's in our fake
loosely,
Earth,
very loosely based on New Zealand. But it's such coarse resolution that you can't really even tell it.